Okay, so if you're watching this on YouTube, welcome to the video. Hopefully I can get these angles correct. So welcome to the channel. This is Math Pond. I am a mathematician. I went to UC Irvine to get my PhD. And, I've just been learning math my entire life. I really enjoy mathematics in general and teaching mathematics, especially algebra and, a lot of statistics stuff, and financial mathematics is really kind of my area of expertise. In my PhD, I did algebraic topology, so a lot of the stuff that I'll be talking about today, if we get into it, is a lot of the stuff, kind of the basic foundations of a lot of the mathematics that I did for my PhD professionally. And yeah, just kind of relaxed channel. I want to stream some math sometimes. Sometimes you'll see, ducks and chickens in the backyard at my house. Sometimes I might stream some chess or something, kind of just whatever I'm in the mood for. But I'm going to try to put out like 1 or 2 videos a week. Should just be kind of basic mathematics for any age groups. Could be children, could be adults. Really, this is just like your foundational mathematics. Let me get rid of these for now. Right, so, the foundations of, how do you solve linear equations? How do you solve, your basic equations like 3x plus 2 equals 7, something like that. So what is the mathematics that guarantees that we're allowed to do this, right? Okay, so I think should be good. In the future, I'll probably try to get the angles a little bit better. Here, I'm just working with my laptop. Maybe I'll get a better camera and put it up higher, but the board here should be pretty easy to read. If there is anybody watching live, you can always type in the chat, contact me if you want to ask any questions, or what I meant was if you want to contact through email, we have our email also, which is mathpondofficial@gmail.com. And if you like my teaching style, or you just need to learn a certain subject, like if you're a college student or something, you can always contact us. We can talk about rates and we can do some tutoring lessons. Or, also I've had people in the past that work as like programmers at big companies, and they literally just love mathematics. They want to learn more. I had one guy, I was teaching him complex analysis. Wasn't really applicable to his job at all. He just was really interested in it. So I know if there's people out there that just really love mathematics, statistics, stuff like that, and you want to learn more, contact us. As well, one other thing that I guess I'll go over is I'll probably have some of my friends as well that are also math PhDs or masters in mathematics, or just math people in general, and they may put out some videos as well, which I'll upload to the channel as well. Okay. So we're still getting situated here, but yeah, so this is gonna be lesson 0. We're gonna begin by talking about monoids. So it's a type of algebraic structure, one of your most basic types. So we'll just call this lesson 0 for now. Hopefully this marker works. So lesson 0, monoids and groups. Yeah, you can see that, right? Yeah. Okay. Right. So what is a monoid? First of all, we're going to need to define a structure that kind of underlies this first, which is a set, right? Hopefully you guys have heard of sets before. Maybe children haven't heard of what a set is, but there's kind of like a technical definition in math, and then there's a simple definition, right? So a set is really just like a collection of items. Usually they're numbers. So we're going to try to define what a monoid is, but first we need to know what a set is. So a monoid is a set. And this set could theoretically just be anything, any collection of like I said, collection of things, but usually they're mathematical objects like functions or numbers or fractions, rational numbers, etc. So a set, is just a collection of things. A lot of the times we'll put it in brackets. It's kind of like visually you're thinking of it as containing the things. So the bracket is around whatever the items are. So usually they're numbers, right? So something like it might contain 0, 1, 2, all the way up to some finite number n. So you could think of like maybe it's just 0, 1, 2, 3. Right? So you have a set with, well, sometimes you go up to n minus 1 because you want the set to actually have n elements. So sometimes we write this n bar. So this is a set with n elements. It has all the elements 0, 1, 2, all the way up to n minus 1. Doesn't contain n. There's some situations in like simplicial algebra and in simplicial topology stuff where you actually want to include n, and then it gets kind of confusing because it actually contains n plus 1 elements, but yeah, not very important. So basically a monoid is, you start out, you have this set and you have this operation on the set. So it's going to be able to, you're going to be able to combine two elements in the set and you're going to get a new element out. So you think of like integers are a monoid under addition because you can take two elements of integers like 2 and 3 and you can add them together and you get another integer 5. So a monoid is a set, right? First it needs to be a set, but then also in addition it has this binary operation. The symbol is not really important. So a lot of the times we just write it as like a star or a blob or a dot, some sort of ambiguous symbol. It could be a specific operation like addition in the integers, and then you would write a plus, but it's kind of like an abstraction of that. So you could think of it's just some arbitrary symbol. It doesn't have to be a plus sign. It doesn't have to be a multiplication sign. It could be kind of like whatever you want it to be. So here we have star. It's a function, and let's call this set S. It doesn't have to be this particular set, but it could be any set S. This is just an example. In general, right, it could be just any things. And it's going to be a function from S cross S or S direct product S to S. And this is another set. So when you have a set S, you can form a Cartesian product, which is actually just pairs of elements from each set. So here when we say S times S, that just really means I have pairs of elements, one from S and then the other one also from S. So here, if it was like 0 through n minus 1, I could have one element might be like 1 comma 2 or something, right? Because you're taking one element from the first set and another element from the second set. And this operation here, star, tells you how you combine those elements to get a new element. Here it's just saying there is a function, but in general, we would have an actual function that's defined, like addition for integers, or another common one is if you have functions from a set to itself, you can compose them, and that composition operation takes in two functions from the set to itself and composes them, and you get a single new function, which is the composition of the two. Right, so basically a monoid is a set. It has this operation, and then the operation has to satisfy a couple axioms, which is just to say that initially it's just a binary operation, but then the binary operation has to satisfy certain properties to actually consider this thing to be a monoid. So really the monoid is, it's not just the set, but it's the set along with this operation, and the operation has to satisfy certain properties which allow us to basically do algebra in a simple sense. All right, so if anybody's watching now, if anybody has questions, hopefully in the future there'll be more people watching, and then I'll have questions while I'm actually teaching. Right, so yeah, we have this set, we have this operation which allows us to combine two elements from the set and get a new element from the set, but it can't be any operation. It has to satisfy these certain properties. All right, so we have our set S. Switch to red real quick. I think this marker's going. Right, so for a monoid, we have a set S. We have a binary operation star, which is a function from pairs of elements in S to S. So we can combine these two elements and it gives us a new element, S. Right, you can see the red, yep. And then it has to satisfy these two properties. So the first property is that it needs associativity of the operation. So associativity of star. So this means that if I take two elements and multiply them together with this operation, and then I multiply another element on the right to that product, it should be the same thing as if I do the product in the other order. Or not the other order, but the applying the brackets in a different order. So what I mean is that if I apply A star B, so if I take two elements A and B, just random, not random elements, but just any two elements A and B from the set S, and I multiply them together with this function star, and then I take another element C, and I multiply on the right by that. So whatever the output of this A star B is, that's a new element in S, and so I can now plug it into star C. So whatever this is, it's some element of S, star C, and the associativity says that if I bracket the stars the other way, then it should be the same thing. So if I do A star bracket B star C, meaning that I do the multiplication of B times C first, and then I multiply A on the left, versus I multiply A and B first, and then multiply by C on the right after. The property that has to hold is that these have to be equal to each other, and if this is true for every element A, B, and C from S, no matter what they are, then we say that the operation has the associativity property. And then the second property is we need there to exist an identity element. So remember before I said, oh, somebody said hello. So before I said that one of the examples of a monoid was if you have a set and you have functions from the set to itself, and you can compose them, that gives you a monoid. And one of the nice functions that you have when you have a function from a set to itself is you just have the identity function, which is meaning that you map every element to itself. If you map every element to itself, that's the identity function, and that's a special type of function. So for it to be a monoid, it has to have that type of element where there has to exist there has to exist, I'm probably going to run out of room, but there has to exist some element which we usually call 1. So there exists some element 1 in S, and this element is special, so if I do the multiplication with this element 1, it basically doesn't change the element. So if I do like 1 times A or 1 times B, I just get A back or I just get B back. So we got a question, is this intermediate algebra? So I mean, right now this is basically the foundations of abstract algebra, but I'm not really going to go too deep right now into that intermediate algebra stuff. We're really just going to stick with simple stuff for now. But I'm glad somebody has a question. So yeah, I mean, I guess this is stuff you would probably learn like later in college in this formal way, but I'm not really going to be doing a lot of like proofs or anything. We're just going to be using this to do some sort of like basic algebra stuff. But if you have questions about intermediate algebra, definitely, yes, I am new. Yeah. yeah, this is the first stream for math for sure. Yeah. So yeah, monoids, just to continue a little bit, but yeah, feel free to ask questions for sure. Are you like a student in college or something? Um, right. So just to continue real quick, monoids. So we have a set, or just to review for a second, we have a set. It has some operation star, and that operation has to be associative, meaning that the bracketing of the operations, it doesn't matter in this sense. And then there also has to exist some element one in S such that, and I'll write it over here. So it needs to have the property that this special element one, if I multiply it with star with any element A, basically I just get back A, which is the same thing as if I do A star one on the right. Like that. Oh, you're a college student? So which, are you undergraduate? Right, so that's monoids. Very basic, just you have some set collection of things, some operation, and the operation needs to be associative, which is a little bit to take in, right? Um, and then there also has to exist this special element one. And a lot of the times we won't really even call it one because it gets a little bit confusing because in certain monoids, with the operation, like under multiplication, the identity is usually one, but under addition, like in the integers, under addition, the identity is actually zero. So it gets a little bit confusing. Sometimes the identity is zero, and sometimes the identity is one, depending on the what the what the actual set is and what the operation is. So sometimes we'll say that there has to exist an element e. So instead of 0 or 1, we just pick a letter e. And sometimes you'll see like e with a little g in it, or e with a little s. And this e is the identity element. It's the same thing, it's just instead of writing 1, we'll just write e here. But e is not just some e is not some any element, it's specifically that identity element. All right, and then so I wanted to just go through, or I just wanted to get that definition out of the way so that we could get to groups. So really, there is a lot of math to do with monoids, but really a lot of the algebra starts with groups. So we're gonna add a third condition to get to groups. So a group is a special type of monoid where you have this associativity property, you have the identity, but also you have inverses for elements as well. So you'll be able to multiply elements on the left or right by their inverse and be able to get back to the identity element, which isn't always possible in a monoid. You could have like functions that map from a set to itself, which are not invertible, for instance, and then there wouldn't exist possibly there's no left or right inverse, and so those elements wouldn't exist in a group. But there is a special thing that you can do, which is if you have a monoid, you can always look at the submonoid of all of the invertible elements, all of the ones that actually do contain inverses, and then for those elements, they do make up a group. So, but that submonoid might be trivial. It may only contain the identity element, possibly. That might be the only invertible element in the monoid. Okay, so that's monoids. You have this set, you have this function, it has these two properties, and then when we get to groups, groups are going to have this additional property that the element is actually invertible, that when you multiply by the element, there's a way to kind of go back and end up with this identity element, this special element. Okay. So yeah, I'm thanks for the one viewer who showed up. I didn't think there would be anybody. Right, so monoids, then we'll talk about groups. And I'm going to try to keep the video to maybe like 10, 20 minutes. I think I'm already close to 20 minutes, so I'll probably wrap up in the next 5, 10 minutes. All right, so now we talk about groups. Right, so a group is, like I was saying, it's very close to a monoid. It's just a monoid plus an extra condition that we're going to have invertibility of all the elements. So group is first a monoid G. Let's see, how do I want to write this? So a set G is a group. Right, so this is just our S from before, but now I'm calling it G since it's a group. So it's some set, and it's a group if it's first a monoid. Well, first we need the operation too, right? So a set G, let me see. Here, a set G with operation star G, which is a map from G cross G, takes two elements of G and produces a new element of G. So the set with the operation is a group. If it's first a monoid with this operation, so it has those first two properties. So it's associative, and it also contains some special element, which is called the identity, which when I multiply every other element, I get back the same element. So first, G is a monoid under this operation, and then in addition to that, it has this additional property. So it's a monoid, and for all G in the group, big G, so all elements little g in big G in the group, there exists some G tilde, another element in the group, and when I multiply G and G tilde together, I get the identity. I get E, or I get, E, EG. So first we have a monoid, and in addition to being a monoid with this operation, it also has the additional property that for all the elements in the group, there exists another element in the group that when I multiply them together, I get the identity, no matter which way I multiply them together. So there exists some G tilde such that, I'll write it again after, but such that G star G tilde equals the identity, and this is also equal if I do the operation the other way. So G tilde star G. I'll rewrite this in a second, but it says G tilde star G, or multiplying G tilde with G is the same thing as multiplying G with G tilde, which gives you the identity element. And this needs to be true for all G. There needs to exist this other G tilde that is basically the inverse. Okay, so basically, so you have a group. A group is a monoid first, and then it has this additional property of all the elements have inverses. And this needs to be true for every element. So no matter what element in the group I pick, there should be some inverse that when I multiply by the inverse, I get back to the identity. Let me just rewrite that bigger so people taking notes or something, they can see it. Right, so group is this monoid. Such that for all G, sometimes you'll see I'll write this symbol, it's like a E, but it just means is an element of in set theory. So for all G in the set G, so for every element of the group, and then this element means there exists. And you can actually prove it's unique here, but we don't need to prove it's unique, or we don't need to state that it's unique for the definition. We just say, for all elements G in the group, there exists another element G tilde in the group with the property that G tilde multiplied with G is equal to the identity. And this is the same thing as if you do G multiplied with G tilde. All right, so basically a group is a monoid and it has inverses. So for any element in the group, there's some other element in the group, and when I multiply them together, I get the identity. And this property really, this is important. So a monoid that doesn't have inverses for every element is sort of harder to work with in some way, because we want our monoids, we want to be able to cancel multiplications or additions to be able to solve equations, for example, like linear equations. I'll just do one real quick to show you what I mean, and like what is the purpose of all this, right? Is this just a bunch of abstract algebra for no reason, right? No, we can do actually very down-to-earth things with this, with a group that has inverses, or a monoid that has inverses, which is a group. And really, if you've ever solved any basic equations with, linear equations with variables, you've implicitly used these properties before, right? So let's just look at, you have an equation such as, I think I wrote down an example here. Yeah, so really what the thing is that we want to use is this cancellation property for groups. Right, so in a group, you're going to be able to when you're writing out your equation with variables, you can add, if it's 3x plus 7 equals 2, you can subtract 7 from both sides and cancel the 7. And that's really, you're using the property of group theory here. So you're using this cancellation property. It says that in a group, and this is really a theorem, so in a group, if A star B is equal to A star C, right? Meaning that if I take an element B and I take a possibly different element C, or, a priori, we don't know if it's the same or not, right? It's just some element B and some element C, they might be the same, they might be different, but we multiply them on the left with definitely the same element A. So we take some element B and some element C, multiply on the left by A, and the theorem says that if these are equal, after I multiply on the left by A and I'm in a group, then that automatically implies I can cancel the A on the left by multiplying by its inverse, and we get that B actually equals C. And this is not true in any monoid. This is only true in monoids that have this left cancellation property. And in particular, groups are an example of monoids that always have that property. So if you're in a group, you can cancel on the left. You just multiply on the left by A inverse. You use the associativity property to group together A and its inverse. You use the inverse properties to say that that's equal to the identity, and then you use the identity property to say that the identity times B is just B. So basically, you can just cancel the A on the left and the right by multiplying by A inverse on the left and the right of the equation. Because if these are equal to each other, then you should be able to plug it into the right-hand side of multiplying by A inverse on the left. Okay, so if anyone's there, do you have any questions? And this theorem is really, this is what we're using. So let me just give you a down-to-earth example here. So where we use the cancellation property to actually solve something in real life. And this is something, that you might do in middle school when you're first learning mathematics, but you don't really learn it this way, although I think maybe you should. So let's solve like an equation such as, so let me just do a quick example here. So we have such as, let's see, I was going to do something else here. Let me change this one a little bit. Yeah, let's just do this one. Yeah. So 2x equals 56, or in other words, 2 multiplied by some number, right? Some integer equals 56. And you want to figure out, well, what is this number, right? I know that 2, when I multiply 2 times the number, I get 56. So how do I go backwards, right? We got a bunch of scammers. So we have 2 times x equals 56. How do I undo this multiplication by 2? Well, I have to multiply by the inverse of 2, right? And there's no inverse of 2 in the integers, but of course, if we're working over the rational numbers and I'm wanting to solve this in the rational numbers, I could multiply by the inverse of 2 on the left here, so multiply by 1/2 times 2x equals 1/2 times 56. And then on the left, 1/2 times 2 can be grouped together with the associative property, and then 1/2 times 2 is equal to 1. So really this left-hand side just becomes 1 times x, which is just x by the identity property, right? Remember, if we multiply any element in the group by 1, then we just get the same thing back. So this left-hand side becomes 1 times x, and then the right-hand side, we can just do the math out. 56 divided by 2 is, what is that, 28? Right, and so that tells us that 1/2 times 2 times x, these cancel, you just get 1 times x, which is x. X equals 28. So you can see this is really how you do basic algebra, right? You're using these properties of monoids and groups every time you solve one of these basic linear equations, or you could have an addition here too, and you're going to be, instead of multiplying by the inverse, you're going to be adding the inverse, which is just subtraction. Okay, oh wow, so that was exactly 30 minutes. So that is good timing. I think I'll just leave it here for lesson 0. This is kind of like a test, like I said. I'll try to make like 1 or 2 of these a week. For now, if it gets more popular, I mean, I could do it more. I really like teaching, of course, like I said. So, and yeah, I might do some chess streams, just playing chess maybe on like Tuesdays or something. So if you like chess and you want to follow me there too, that's cool. I missed it. I think I'm just gonna stop the recording here so I can